Okay, Alban, the virtual floor is yours. Please go ahead.
So, hello, as Jakub said, my name is Odot Alban. I'm a Ph.D. student at Inria Nancy, but actually located in Strasbourg. I will present to you the result of my last accepted paper. So it's about how to improve the prediction of a neural network that takes as input external forces and provide the displacement field, the resulting displacement field. Oh, cannot change slide. So we'll first start by a bit of context on why we did that, and we will see what were the contributions, and finally we will discuss the results. So we know, I mean, pretty much everybody knows that the finite element method is quite common in the continuum mechanics. We usually compute deformation using classic software such as SOFA or Wolfram Alpha, I guess. But it takes a lot of time to compute simple deformations, and yeah, this is it. And we want to leverage the approximation capability of the neural networks in order to perform this kind of computation in real time. For example, in the context of computer-assisted surgery, the surgeon cannot wait 1 hour for the computation to end, so we will need faster solutions. So in the case of deep learning, there are two main fields: the physics-informed neural networks that actually provide the formulation of the physical phenomenon that you're trying to solve within the loss function or the cost function. So the nx here. This has a lot of advantages since you don't need to acquire or generate data in order to train the network, but it also converges very slowly since it doesn't have a ground truth, so it explores the solution space a bit blindly. And there are the data-driven learning process where on the opposite, we converge faster, but we require a lot of data in order to approximate the solution. So as mentioned before, we will have as inputs the nodal forces on the surface, I mean, on the whole mesh, but we will only apply forces on the surface of a mesh because you usually interact with objects with the surface and not with the direct volume. We will pass it through a fully connected network that is the simplest possible architecture. That is basically exactly this one with n neuron-wide layers. And the output will be the nodal displacement. So the goal here is to be able to learn complex hyperelasticity laws with accurate enough deformation. We also want to handle various external forces. By this, we mean that the training will not, for example, only be able to modelize stretching or pulling or torsion. We want to be able to mix a bit of everything to have a more general use case. And we also want to minimize the size of the dataset, because when we minimize this size, it means that we require less samples to train. And also, well, I mean, a physically correct solution. We'll see that it's not exactly the same as the first point here. The physically correct solution implies way more strict errors than the simplest accurate deformation. And also we will guarantee solution validity using a solver after this. And we qualify also real-time deformation as being 60 plus FPS, but I mean, we will see that it's quite easy to achieve this. So first we will see how we modified and use the Newton-Raphson algorithm, and that we call the hybrid Newton-Raphson algorithm, to guarantee the validity of the solution. And in the result, we will see that we improve the robustness and the conversion speed of the algorithm. For the dataset generation point, we will see that we will use the deformation modes of the object. This will allow us to easily compute very complex deformations and also minimize the size of the dataset. Well, I mean, when we say minimize, we will greatly reduce the size of the dataset. So it's not optimal, but it's still a great reduction. And finally, we'll present the physics-aware loss function. That is not exactly the same as the physics-informed neural network mentioned previously, but it's using another formulation of the physics law. Okay, so we will first consider only the blue lines of the Newton-Raphson algorithm. So, yeah, as I just said, if you only consider the blue lines, you get the classic Newton-Raphson algorithm, where we set an initial condition. Do you see my mouse? Or
yes, we can see
okay,
your mouse.
nice. So if we consider only the first line, we set the initial properties of the system to have a null displacement. So we work at the rest shape. And then we compute the Jacobian stiffness matrix, the tangent stiffness matrix, sorry. The residual forces, we solve the equation for the displacement. And then we iteratively modify the position of the object, in our case the beam, but it works on anything. And we modified it, the solver, in order to have a first computation of the residual forces. So the residual forces are internal forces, external forces minus internal forces. And since we are at the rest shape in the beginning, the first one is only external forces. We predict a first displacement using the neural network from those external forces. And this gives us the first approximation of the final displacement. If this approximation is very good, then we don't need to enter in the Newton-Raphson because we already reached the equilibrium criterion. And if it's not, then we enter the Newton-Raphson algorithm. We do a first iteration, and we compare the state after the first iteration to the state after the prediction, the state of the system, sorry. And if the network gives a better solution than the Newton-Raphson, then we continue the iterations with the prediction of the network. So this guarantees the validity of the solution if you put in a system. And we'll see that the guess of the network is usually pretty good. So we skip a lot of Newton iteration, even though we still do a couple of them. Okay. So that was about the Newton-Raphson algorithm. Now about the dataset generation. From our testings, naive sampling requires around 400 forces per node. So if your surface has 200 nodes, it quickly grows to an undoable, dataset generation. And this is only considering one node at a time. If you want to apply forces on couples of nodes, it grows way too big to be computed. So the idea behind the dataset generation is that we will use the deformation modes of the object in order to simply sample the space of deformation. So we go back from this equation that was the line 11 of the algorithm, as you can see here. And we make the eigen decomposition of this matrix K, which is the tangent stiffness matrix. And so this matrix represents the properties of the object, the mechanical properties of the object. And we know that if we work at rest shape, so K equals 0, we will have linear approximation of the final displacement. And that's what we basically do in here. So we consider eigen decomposition. This in blue is a single vector, and we consider only the first few modes of the vector. And we'll see a bit later that we achieve very interesting deformation with only considering the first 3 to 5 modes of this Q vector. The value usually range between -1 and 1 for each of the 3 coefficients, and you just have to sample them. I mean, usually in my dataset, I put linear spacing between -1 and 1 for each coefficient, and I take random samples. Random coefficient in those spacings. So from our tests, we went from we consider beam composed of 1,700 3D nodes, and we went from a dataset that was composed of 680,000 simulation to around 5,000 simulations, for the same result. So it was so we went from 8 days of computation to only generate the dataset to around 1 hour and 20 minutes. So it's quite a good improvement, I guess. And this is the type of deformation that we can generate using only the first 3 to 5 modes of the Q vector. Here it's only 3. So you have a huge nonlinear deformation with twisting, which is very difficult to reproduce when you try to use the naive sample approach, where you pick random nodes on the beam and apply a random force on it. So here we have nice control over the distribution of the dataset. And finally, I don't know how long I have. Finally, I will present the physics-aware loss function. So commonly, in deep learning, we are working with the mean squared error when we deal with regression problems. So the formula is presented here. So it's the square error of the normalized square error of the output of the network compared to the ground truth. It has nice properties such as the quadratic convergence, but for same error, there is a lot of distribution that produce the same MSE, and not all of the distribution are physically correct. For example, here on the left you have what we will consider erroneous but good prediction, so it's quite smooth. And on the right, you have okay prediction if you look at the MSE, but if you look at the physical properties, it's really a mess. So we want to enhance this mean squared error loss function with some physical knowledge to differentiate between the left case that we want, even though it's quite wrong. The solver can easily correct this approximation from the bad prediction, where the solver will not converge if if we give him something like this. Okay, so the idea, if you remember the equation, the 11th lines of the Newton-Raphson solver, we had a k of u times the displacement equals the residual forces. So the residual forces is the internal minus the external forces. We will use the norm of this vector, which represents the remaining forces in the system. So it's a 0 when it reaches equilibrium, and it's a huge value when it's not equilibrium. And we normalize it by the external forces. I mean, we divide it by the external forces to take care of the, well, I mean, to remove from the equation the, for example, the Young modulus of the system, because this can grow very quickly with huge Young modulus. So basically, we multiply the MSE by the residual divided by the external forces. This for two MSE of the same value, but with different displacement, you will have different residual. So this helps us differentiate between those two, the good prediction and the bad prediction. So now in terms of results, we will use those two models. So on the left, we have a propeller with that is 1 meter by 1 meter by 1 meter of 0.5 meter of 8. And this one is a 100-meter long beam by 25 by 25 meter, with a very different hyperelasticity law and Young modulus. So when we compare the results first of all, we achieved the goal that we set about the accuracy of the prediction with 2.1% error and 1.7. So we set the goal to be around 2%. So it's quite nice. And yeah, and the max error is in the worst case over 100 forces, it was 6.1%, and it was on a very small displacement, which can quickly make the relative error explode. So we remain pretty confident over the results of the network. We see also that we achieve quite easily the real-time criterion of 60 FPS with 0.4 millisecond per prediction. So that's cool. And when we compare the results, so we can compare the first and the last line. When we compare the results between the physics-aware loss function and the classic MSE, we see that we have a fourfold improvement in the mean error, and yeah, and we also improve quite significantly the max error, and yeah, and the prediction time remain unchanged, obviously. Considering the Newton-Raphson robustness, so as mentioned, we improve the robustness of the algorithm, since we give to the algorithm a pretty good first guess over the solution. So the prediction is picked every two prediction, I guess, and it converge 99% of the time, where with the same data set, it usually converge 68% of the time. Sorry. So yeah, the Newton-Raphson algorithm is known for not converging quite quickly when the conditions are not good, and usually people apply load steps of forces and in order to remain in the convergence area of the network, and that's what we do in the next slide. So we apply the same forces as in the previous test, but with load steps. So when it does not converge with a single step, we apply 2. When it doesn't converge with 2, we apply 3, etc. So the classic Newton-Raphson usually converge in 9.1 iteration on average, where with the hybrid Newton, we managed to converge in 5 iteration. So that's pretty good. And we also have a standard deviation, which is basically reduced by 4.2, by a factor of 4.2. So that's also pretty good for our case. And thank you for your attention. Sorry for being late first, and if I take a bit more time than that was expected.
Not at all, Alban. Thank you so much for your presentation. And let me open the question or discussion part of our seminar. I have a couple of questions, but I will leave the floor for others. Just switch on your mic and start asking. Okay, just maybe I will start first. So I see a great potential of your methodology, especially as a first guess for the Newton-Raphson method, as you shown in one of the examples exactly here. Perhaps there should be not U1 in this line 14, but UK perhaps, and the same in the line 13.
We compare it when the k equals 0, so it's U0 plus 1 here, so it's already U1.
But... so you only compare it for the first iteration?
Yeah, I only compare the first iteration because the prediction will remain the same with the external forces. So.
Okay, now I can see it. I see. All right. Yeah, and I think this is especially suitable or good where for the cases in which require multi-step loading procedure for your finite element method, because even for hyperelasticity, for some loadings or some problems, you need to have a multi-step loading in order to reach the final deformation, which can be very, very big.
Yeah. For example, for this deformation, I applied something between 15 and 30 load step, but the neural network will only see the initial forces and the final displacement, so it can. I mean, we do not provide all of the intermediate step, so it provides the final solution, and we can skip.
Exactly. So the improvement is even higher maybe than you shown, because you shown that usually it requires 9 iterations, but if you just take into account all these steps that need to be made.
Yeah, the dataset for this results was not with the deformation that I showed earlier. It was with a very, something like half or a quarter of the type of deformation I showed in the picture.
This average number of iterations, does it include all steps that are required to converge?
Yes, it does, but it was something like, I think in the dataset that on which I trained for the article, I only put something like 4 load step at maximum.
I see.
So the deformation were less non-linear, if I can say something like that.
Okay, and in the slide 11, if you can go there, so you have. I just want to understand what sort of loading did you have? Did you have a localized force loading?
So I don't know if you can see here. Maybe we cannot if you ask, but there are some arrows on the.
Okay, so it is a distributed loading.
Yeah. So basically, what I do is so I use SOFA, and I put so I set up my mesh, and I select 100 random boxes over the mesh, 100 random spheres around the mesh, and also at some point I will generate very local forces, and I just generate a force using the Q vector and mask with the box or the sphere or the index choice.
Okay. And maybe if you could elaborate a bit more about this physics-aware error function that you use. It was slide 14 maybe, or 13, I don't remember.
I don't know why it's zooming like this. Okay. Yes.
Maybe 14. Yes, exactly.
Yeah.
So this is not a standard error function that you normally use in the supervised training of your neural network. You have some additional term R, which is this physics-based, which expresses your balance equations.
Yeah.
Yes.
So basically, when we compute the solution of the Newton-Raphson algorithm, we compute this right-hand side member, that is the residual forces, difference between internal and external forces, and we know that this vector reaches 0 when we reach equilibrium. So the norm of this vector is actually a criterion of the solver. If I can go back here, as you can see, line 17 and also line 5. And we know that this criterion is very sensible to the displacement that you give him. So for two similar errors, you will not have the same. Well, I mean, you can have a 1,000 scale of 1,000 between two similar MSE error compared with the residual. And so this helps us to converge towards physically correct solution, since at the end the error is pretty low, but this factor keeps on multiplying, scaling the loss to tell if the network is doing a correct approximation or not.
I see. But what I don't, let's say, fully understand is how do you compute the backpropagation in your neural network? Because normally you need to compute the gradient of your error functions with respect to the some weights parameters of your neural network. And for MSE, it is a straightforward task to be done. But for R part, I don't know, because then if you apply the chain rule, then you get what? You get some...
you get the, I mean, since it's multiplication and not an addition, it keeps on scaling the MSE gradient toward the during the backpropagation.
So you don't apply the full chain rule, right? You keep R as a constant. That
yeah, it's I mean, it's constant per batch, but it's not constant for the whole training.
I understand this, but for computing the gradient, if you have a gradient descent method, so somehow this gradient descent method normally should be somehow aware in which direction to go to reduce this residual part of your error function. This is how I understand it. And my question is whether you compute this gradient with respect to R of u, or you keep this R of u constant for computing gradient.
No, this R of u constant is just a float. That so it's not a part of a tensor or anything. So it just scales the MSE, and the gradient is only computed on the MSE. So this one scales the gradient also. So
how can MSE know in which direction to go to minimize R? This is like done by the chance that at some points you reach the
When the thing is that so for two similar prediction, the scale will not be the same at all. So one will have let's say a bigger error than the other, and so the backpropagation will improve better on the one that produced the minimum error from the one that produced the big one.
So you mean that once you enter the zone in which R is low, your residual is low, your gradient will be lower because R will be lower. It will be scaled by R. So you will be not that easy to go away from this region because your gradient will be shorter. So you will start searching for your solution near that zone, which is
cool because I mean that's what we want when the prediction is physically correct. The residual is close to zero, and when the prediction is not physically correct, the residual is big, so the gradient will tend to leap over this. Maybe I mean that's the guess. It leaps over this local minima if it can, and just continues a bit further. So that's the idea behind this. That it helps getting away from those attraction points.
Okay, I see. Vasilis?
Yeah, hello. Sorry to interrupt, but I have a question on this subject, and I thought I would just pop in. First of all, Alban, thank you for your presentation. It's really nice. But like now I hear you discussing about that, and I was thinking about that. So you add some physics-aware term in your MSc, and your intuition is that there is the possibility that MSc could be low, but the physical solution could be, let's say, wrong. So you add this second term to make sure that physically it makes sense.
Yep.
And I do wonder, so that means that MSc could be low and RU can be high. So in the end, the loss function will penalize that more, and the network will try to reduce the residual more, let's say. But is it possible to have the opposite thing, to have an MSc that it is small and an R term to be high, and in that case, so it is possible that, and is that a desirable effect or an undesirable effect, or we don't care about that?
So yes, this is definitely possible, and that's what we see. I'm trying to find a picture that I got not so long ago. So I was trying to yeah, this is the one that I want. Can I share the picture now? I have to stop sharing this one and
no, we saw it.
Sorry.
We saw it.
Sorry.
Okay. Because I think you are sharing your screen, the whole screen, so we can see whatever you can see on your screen.
Oh, okay. Okay, yeah. So this is the so the values are not good because I scaled down to have a proper view of the phenomena. But here we have the rest shape. Here we have the residual in Z. So this is the approximation of a linear approximation of the final displacement. So imagine a beam that has some bending in it. Here will be without noise and without at rest shape, and here will be without noise, and the final deformation. So we can see that the residual grows, and then at some point here it's 0.5. It starts to reduce, and this is, I mean, it's not a desirable effect, but what we can see is that I don't know if I still have the script. I didn't take a screenshot last time. But
But
at
can you
this
tell again what this plot is showing? Because that is the residual, right?
yeah, in Z is the residual. In X, it's the linear approximation of the final solution. So it's between 0 and 1. So I basically put the rest shape plus alpha times the deformation. So
And why the residual have two zeros? Like
because at rest shape there is no internal forces, so the residual is only the norm of the external forces. So it's not zero. It's a very dim force. It's not exactly zero, but it's pretty close to zero.
So this is the case for the force zero. Also, the loading is zero here.
Yeah. Well, if the loading is zero, the residual will always be zero unless you modify the position of the.
So the loading is constant, but you are modifying this positions, the solution, or?
Yeah, exactly. So I'm applying a force at the tip of the beam, let's say, and I just change the position of the beam by either interpolating the final solution or adding noise. So on the y-axis here, it's the noise, and on the x-axis here, it's the interpolation between the rest shape and the final deformation.
So these are only the internal
Yeah.
parts.
So
This
is the internal part.
It doesn't include the external forces. That's why you have zero in the. Okay, I see.
Yeah. So basically, as you can see, the residual will be very low in the beginning, and also when we reached equilibrium. But the fact is that usually in the beginning, network produce pretty much only noise. So we will be on this part of the curve with high enough residual. And I didn't meet yet the case where the prediction was terrible, but the residual was low. So, but it can happen. For example, if we have the perfect set of weights that values almost at zero everywhere, and the initial deformation is null, then we will have a very low residual that will provide a very small gradient due to the formulation of the loss function. But I never met this case because usually it's just a big noise in the beginning. So,
but again, in your formulation that you showed us on the slide 11, I guess, no, but 14. This residual is the full residual that includes the internal and external forces.
Yep.
Okay. And okay, so this is not like in the plot you showed only the internal forces.
Yeah, but I mean it's pretty much the same since it will only scale up the. It will only raise the residual by the norm of the external forces. It's just a vertical displacement, so the curve will stay the same. Just there will be no zeros
in the beginning, but there will be zero in the end, right?
Yeah.
Okay. And do you think that, let's say, just sticking to this equation number 5, because now I started to understand this very idea, why not to do the full linearization or compute the full gradient of your formulation, because it is a trick that you are doing that even though you are computing your back propagation only for this MSE part with some scaling factor that is coming from the residual.
Yep.
Even though your learning procedure of your neural network is able to find finally the solution that is representing the solution for small r of u, or small residual. And the mechanism that is playing the crucial role is that for high values of your residual, of norm of your residual, you will have longer gradients. So your increments in your teaching procedure or training procedure will be higher. And then once you will reach the point for which the residual is low, the increments will be quite small.
Yeah. So we stay in the good part, and we try to leave the bad parts of the
unless you will have bad luck and you will end up in a solution that is completely wrong, but will be good if from the point of view of
So basically, if you let's say you use the fully connected network as I did, remove the biases and put 0 as initial weights. You will stay with a network that produces zeros because the residual will be very low, will be equal to the external forces, and which can be, I mean, since we divide it by the external forces here, you will only provide ones, so we will not move away from this place. I mean, not fast enough. So we probably stay in this zero area of the network.
I see.
But it's very special case because the probability that all weights equals 0 is it's very low.
Okay. So your R of U also includes the forces, because normally let's say R depends on U and also some external forces, right?
Yeah, the residual is both external and internal forces.
So it should include some input data as well, right? Normally for your neural network, prediction, your UP that you call UP, I think, the prediction, the argument is your force vector.
Yep. So it's force vector computed from the null displacement, so it's only external forces.
External forces, exactly. Okay. Now I understand it much better.
I did not see this. Okay.
And what tool did you use to implement this? TensorFlow?
It's
libraries?
all written in PyTorch, and the physics interaction is done with SOFA. So we can access the data in the middle of the solver, etc. It's pretty easy with SOFA.
I see. So you do this, right? Because you could, if you have your data set, you could imagine that you cannot prepare your data set in advance for R because you need to compute it for any possible prediction.
Yeah.
I see.
So the whole time I have to interact with the solver during the training, but computing internal forces is not what costs a lot of time, so it's okay. We don't add too big overhead.
All right. I understand it. Thank you. Any more questions?
Yeah, would I be right to ask a question?
Okay, go ahead, Jack.
First off, thank you for the presentation, Alban. Really interesting, a nice mix between physics and data-driven models. I was curious about have you tested out different complexity of physics models for your predictions? So you specified that you used hyperelastic models for your predictions. There are a few different kind of hyperelastic models, and are you assuming that your material is entirely isotropic? Because given the application of computer-assisted surgery, a lot of biological systems are anisotropic in a lot of places, and I was just curious if you've sort of tested that out at all.
So I didn't test any anisotropic material yet, because I don't know if there is a public implementation of anisotropic materials in SOFA. So, and I'm not, I mean, it's not my subject, so I'm not prone to implement them. But I tried on multiple hyperelasticity laws that were publicly available in SOFA and achieved similar results, even though it converged faster with the Savenon-Kirchhoff than the Neo-Hawkian due to also the data that behaves, the simulation that behaves a bit better with Savenon-Kirchhoff, because Neo-Hawkian is very sensitive to element inversion and compression, for example. So yeah, I didn't try with very specific materials, only the one easily available.
Okay, thank you very much.
Hi Alban, can you hear me?
Yep. Hi.
So just an answer to Jack, we will soon release some new material law for SOFA that will include anisotropy, so it should come quite quickly in the summer if you want to try it soon. So my question is that you have to design every simulation in SOFA, or it could be done on every different software?
I mean, it could be easily done. I mean, not easily, but we use a framework that is called Deep Physics. So it's a deep learning framework, and this one doesn't depend on SOFA in any place. I mean, we use SOFA as a scene, but it could be anything else. What we need is to be able to implement and interact with the solver in Python in order to provide the network prediction somehow to the solver as initial guess, and also being able to get the residual forces in order to compute the loss function.
Okay, but in deep physics, what are you providing? Like you give your mesh, and then you give the forces you want, I mean, the range of forces you want to apply on the object. How does it properly work?
Deep physics is just the deep learning framework, and so it's just a SOFA scene that runs and sends data to deep physics. And so I mean, deep physics doesn't do anything besides requesting data to the SOFA simulation. And basically, yes, in the SOFA simulation, maybe I can show not this. Maybe I can show. Okay, animate begin. Yep. This is.
Can you make the fonts a bit larger?
Yep. Yeah, I will zoom in when I have the. How can I? I don't know. Can I do this?
I think if you do like a control zoom, I mean control and petite molette, should zoom in maybe.
I tried, but it doesn't work. So window. Well, maybe I can simply do something like this.
Good.
It doesn't even work. I don't know if it's zooming or not, but view. Okay.
No, but for me, I can still read it a bit small.
Yes, it is much more legible now because
okay. So basically, so as mentioned in the presentation, basically what happened is that I generate my Q vector, which is full of 0 beside the free first coefficient, multiplied by my phi matrix, and this gives me a force that on which I apply a mask, which is the indices selected by the random boxes and spheres. And then I simply have a component in SOFA that generates external forces, and that apply external forces, in which I write my force.
Okay, and how do you find the amplitude of the forces?
The amplitude of the force is given by this product, which is Q. I mean, Q has the free first coefficient of Q, the range between -1 and 1. And since the phi matrix is constructed using the physical properties of the object. It's automatically scaled by the object. So the force will be scaled by the Young modulus, I guess, if you use something like Saven or Kirchhoff.
Okay. And so did you try to use more or less modes, like to see if there was a big change between 2 modes or 5, 10?
Yeah, after, the first 3 modes provide very good deformation because it's usually what you think the object can do intuitively. So for example, for the beam, it will be vertical bending, lateral bending, and twisting. And if you go to the 4th, 5th, 6th, etc., you will start to have this kind of double bending where it's bending to the left at the base of the beam and to the right at the tip, etc., etc. And if you go too deep in the deformation modes, the neural network has a lot of problems with this. It starts to, start to not be able to approximate the solution. But if you use the naive approach, also you will never see this kind of deformation. So it's a problem, but it's not completely due to the method.
Okay, so yeah, if one day I want to run to create a training set, I just have to give you just a geometry, that's all.
Yeah, and the physical properties, the law that you want to apply on it, and yeah, it's in one script I can generate the whole dataset.
This one is available on GitHub with this deep physics module?
No, it's not yet available. The training scenes are not available, but you can have the maybe maybe we can. Sorab will have some similar code very soon because we plan to try some things like this with Sorab.
Okay, well, thank you. It was really interesting.
Thank you.
Thanks. So just a comment about your data set. So you used only this long wave modes of force profiles, right? So you just which exclude the localized forces, or
that's why in the code so I generate forces, and I have 33% of my data set that is applied on very localized forces. So I pick n random indices on the beam and apply the force that I computed here. So it's I still have a third of my dataset that are local forces.
Okay, this is very, very nice project, I guess, that you have mixed. Mixed. All right. All right. Thank you so much to you for the presentation, and to everybody for your attention. The meeting has been recorded, so everybody can listen to it in the future, especially those who couldn't attend it today. Thank you so much. Have a nice day, and we'll see each other probably in 2 weeks. I haven't managed to fit all the meetings week by week, but I have a promise from somebody to show a nice results and nice approach within 2 weeks. So hopefully I will send you the invitation soon. Next week. Again, bye-bye, thank you, and let's stay in touch.
Thank you for inviting me. Bye-bye.